Welcome to section 3 of Unit 1, and in this section we'll be looking at Introduction to Integration. By the end of the session, you will be able to appreciate the concept of integration. You'll also be able to determine the integration of a function, such as f of x or f of y. What is the area under y as depicted in this particular graph? How would you be able to determine the area of this particular graph? Now, it becomes easy to do this with the help of integration. You can determine the area of this, but how accurate would that answer be? So we can start by breaking down our area into smaller pieces. So we start to look at smaller pieces of this, and then when we are done, we cannot add them up as a whole. So here we look at the area in bit by bit, and then we break it down further again until we're able to get it as a whole. Now, as the slice approaches 0 in width, the answer approaches the true answer. So integration and differentiation are the reverse of each other, which we made mention of earlier on. For example, what is an integral of 2x? We know that the derivative of x squared is 2x. So an integral of 2x is going to be x squared. So this is basically an illustration of the difference or the similarities between differentiation and integration. So I have a function x squared. When I find the derivative of that function, I'm going to get 2x. I have another function 2x. When I find the derivative of 2x and the integral of 2x, I'm going to get what? X squared. So you will see more examples later. Notation. When we are representing the integration of a function, we use the stylish s. So this is the stylish s we are talking about, which actually means the sum of, or the idea of summing slices together. So the notation for integration is represented by this symbol. So this is the integration symbol. This is the function we want to integrate, and these are the slashes along the x-axis or the x function we are trying to integrate. And we can write the answer as x squared plus c. Now, why plus c? We wrote the answer as x squared, but why the plus c? It is the constant of integration. It is the constant of integration. It is there because of all the functions whose derivatives is 2x. It is not only x squared that will give us a derivative of 2x. So there are other functions that might have given us the same derivative. So that c there is for all the functions that have a derivative or whose derivative is 2x. So the derivative of a constant is 0. So when we reverse the operation to find the integral, there could have been a constant of any value. So we wrap up the idea by just writing plus c at the end. So as depicted in this example, we realize that the integral of 2x is actually x squared, but we also have x squared plus 4. We can also have x squared plus 3. We can have x squared minus 6, because the derivative of all of these functions will give us 2x, because the derivative of any constant is 0. So if I find the derivative of this function, I'm going to get 2x. This will give us 2x, and this will also give us 2x. So to represent that there is a constant of the differentiation, then we always include plus c, which is the constant of integration. So that constant over there represents all the derivative or all the functions whose derivative might have been 2x. Now, integration is like filling a tank from a tap. The input before the integration is the flow rate from the top. Integrating the flow, adding up all the little bits of water, gives us the volume of water in the tank. As the flow rate increases, the tank fills up faster and faster. With a flow rate of 2x, the tank fills up at x squared, which is the derivative. So you realize that derivative or differentiation and integration are the reverse of each other. So we have integrated the flow to get the volume. So looking at these two diagrams, we have x squared and then 2x. So this is more like the differentiation. We have the smaller pieces that are going to add up to make up the whole. So this is the differential of the function x squared. And here we look at the tank here, where all these pieces have actually added up to form what is in the tank here, which is the integral of the function 2x. So integration and differentiation are the opposite of each other. So we can do the reverse too. Imagine you don't know the flow rate, you only know the volume is increasing by x squared. You can go in reverse using the derivative, which gives us the slope, and find that the flow rate is actually what? 2x. We can write that down in this way. We have the derivative, the integral of 2x dx, which will give us x squared plus c. And like we said, the c is a constant of integration. And the slope of the volume increases x squared plus c, which gives us back the flow rate of dx over d over dx, which is the derivative of x squared plus c, and that will give us 2x. And here we can even get a nice explanation of that c value we've been talking about. Maybe the tank already had water in it. The flow would still increase the volume by the same amount, and increase in volume can give us back the flow rate. So this is already, so to better explain this here, we already have some volume of water in the tank. However, that does not affect the rate at which our water is being added up, or the flow rate. So the fact that you have some quantity of water in the tank does not affect the flow rate from our tap. So there might have been water inside there. It doesn't mean that all the water from the tap is what actually made up to that quantity. There possibly could have been water in the tank before you started filling it up. So differentiation is the opposite of differentiation. So integration is a way of adding slices to find the whole, and integration can be used to find areas, volumes, central points, and many useful things. So when you have, it is important to note that when you are finding the integration of a function, don't forget to always bring the constant, which is represented as c.